In this video, we solve problem number 4 from one of the quiz number 2s from the elementary differential equations class in the spring 2021 semester at Tulsa Community College. We're asked to show that the differential equation below is not exact, and then we're told that the differential equation can sometimes be made exact by multiplying the differential equation by an integrating factor of one of these forms. Then we're asked to modify the DE so that the resulting DE is exact if that's possible. And if it's not possible, explain why it's not possible. Now, this may not have been on your quiz if you're taking my class this semester. There were different forms of this quiz. This is the form of the problem on one of the quizzes, or this is the form of problem 4 on one of the quizzes. This may or may not be a problem that you've seen before. Okay, let's do this part first. It says, show that the differential equation is not exact. Well, a differential equation written in this form is exact if this derivative of this function with respect to y is equal to the derivative of this function with respect to x. In our class, we're labeling this function m of x and y, and we're labeling this function n of x and y. We just need to show that those partial derivatives aren't equal to each other, and then we know that the differential equation is not exact. So we'll just compute those partials. And then we'll show that they're not equal to each other, which would mean that the differential equation is not exact. So m is cosine of x. So the partial derivative of that function with respect to y, that's easy enough. There's no y's in it. We're treating x as a constant. That means cosine of x is a constant as well. Derivative of this constant with respect to y is 0. And n of xy in this case is 1 plus 2 over y times sine of x. And we want to take the partial derivative of n with respect to x. We're treating y as a constant, so we bring the constant down, or just write it down, and then we'll take the derivative of this function with respect to x. Derivative of sine of x is cosine of x. Obviously, 0 is not equal to that. So right now, the DE is not exact. Now, we're asked to make the differential equation exact if we can. Now, the only way that we can make the differential equation exact, at least with the methods that we're familiar with in this class, is if this function is a function of x only. If this function is a function of x only, we have an integrating factor that's a function of x only. If this function is a function of y only, we'll have an integrating factor that is this function of y. But if this expression involves x and y, or this expression involves x and y, we can't get either one of these, and we would have to solve a partial differential equation instead. We did the derivations for these in the videos over exact differential equations and that's on the elementary differential equations playlist if you want to watch it, if you're wondering where these come from. So we may or may not be able to multiply by an integrating factor, but that's entirely determined by the expressions here and here. If this is a function of x only, we've got an integrating factor. If that's not a function of x only, we'll test this one. If this is a function of y only, then we have an integrating factor. So let's see. Notice that the partial of m with respect to y is 0. And we've got a difference of these two partial derivatives in the numerator here and in the numerator here. So for the first one, you're doing this function minus this function. So it's the 0 minus that one. And then we divide by the function n. So we have 0 minus 1 plus 2 over y times cosine of x divided by y, which was 1 plus 2 over y times sine of x, I believe. I said divided by y, divided by n. Let me make sure that that's right. Yep, that was our n. And these reduce. That's actually really nice. That's a function of x only. So we've got negative cosine of x over sine of x, which is negative cotangent of x. Okay. And so that is a function of x only. Since it is a function of x only, we have an integrating factor in terms of x. So in order to find that integrating factor, we will evaluate the integral of this expression. Now you've got options. You can just apply your cotangent of x rule if you remember that. Or if you don't remember the cotangent of x rule, you can think of this as cosine over sine and do a u substitution. So if u equals sine, du would be cosine of x dx. So this would be a negative 1 over u du. So we're going to get a negative natural log of the absolute value of u, which happens to be sine of x, plus c. Or you could say, oh, I remember the rule for cotangent of x. It's negative, or it's natural log of sine of x. Either way would be fine. Okay. So that is our answer. We want only a single integrating factor. So we're going to choose c equals 0. And the integrating factor is e to that power. There's an implied negative 1 out front. You can bring that inside. And so we get this. And so that'll be 1 over sine or cosecant of x on some interval where obviously sine of x is non-zero. So on some interval from like a multiple of pi to the next multiple of pi for some particular integer n. Of course, that would depend on an initial condition if we had one. So our integrating factor is this. And let me outline what we just did. First, we computed this. Since it is a function of x only, we know that we have an integrating factor. So we have an integrating factor in terms of x. So then we compute the antiderivative of that expression. And then we define the integrating factor to be e to that power. And that is what we should multiply the differential equation by to make the differential equation exact. So it says, if possible, modify the dE so that the resulting dE is exact. If it's not possible, explain why. Well, if this function was not a function of x alone, we would evaluate this expression. If this expression was a function of y alone, then we would evaluate this expression. If neither of those are true, we would say it's not possible. But this time, this one was a function of x alone, so we'll use this one as the integrating factor. So we're going to take this differential equation, we're going to multiply by the integrating factor, which is 1 over sine of x or cosecant of x, whichever you prefer. I actually prefer to write it as 1 over sine of x right now, because we're about to multiply it by a cosine, and the differential equation looked like this. So if I take both sides of this equation now, and I multiply by 1 over sine of x, these reduce, and we get this. Cosine over sine is cotangent of x, and then we have a 1 plus 2 over y times dy there. This is the new differential equation. call it DE star. And we were asked to modify the DE, and then we're done, because that's all we were asked to do. Now, we were not asked to verify that this differential equation is exact, but I'd like to verify it. So I'm going to call this my new M, so I'll call it M star, and this my new N star. The partial of M with respect to Y, the new M, well, there's no Y's in that, is 0. And the partial of the new N with respect to X, well, it has no X's in it, so that's 0. Since those are equal, the modified differential equation is exact. Now, you were not asked to do that, so you don't have to. You were just asked to find this. And then that would be the answer to that part. And you were not asked to solve the differential equation either. You were just asked to get to this point. Okay, so that's how we do that. We just compute the partial derivatives, show that they're not equal. That means the differential equation is not exact. Evaluate this expression. If it's a function of x alone, evaluate the integrating factor, find it, and then multiply the DE by it. Evaluate this expression. If that doesn't work, evaluate this expression. If this is a function of y alone, then this would be your integrating factor. So you'd find it and you'd multiply the differential equation by that. And then at the end, if you want, you can check your work by computing those partials again with the new M and the new N and seeing if those are equal to each other. They should be equal if the resulting differential equation actually is exact.